A star can sneeze, and when it does, the universe flinches. In late 2019, Betelgeuse hurled out a bubble of plasma several times heavier than the Moon. The gas cooled into dust and dimmed the star by more than 60%, sparking fears that a supernova was imminent. But it never exploded. When the light returned, its 400-day heartbeat had vanished, replaced by a pulse twice as fast. Then, in December 2024, astronomers discovered another star moving through its atmosphere. If you don't mind, please give me a subscribe. Now we begin to explore. Betelgeuse marks the right shoulder of Orion, a constellation so recognizable that nearly every ancient culture on Earth gave it a name. The Egyptians saw it as Osiris, god of the afterlife, watching over the souls of the dead as they journeyed through the underworld. Aboriginal Australians called it a hunter tracking prey across the sky, part of stories passed down for tens of thousands of years. In medieval Europe, it was the giant warrior standing guard over the winter darkness, a beacon for travelers and sailors navigating by the stars. The name Betelgeuse itself comes from a mistranslation that stuck for centuries. Arabic astronomers in the 10th century called it Yad al-Jawzar, the hand of the giant. But when European scholars tried to read the Arabic script centuries later, they misread the letters and wrote Bet al-Jawzar instead. The mistake was copied into star catalogues printed in books and repeated so many times that it became official. We've been calling it Betelgeuse ever since, a name that literally means nothing, built on a scribal error from 1,000 years ago. Finding it is easy even from light-polluted cities. On any clear winter evening between November and March, look for 3 stars lined up in a row. That's Orion's belt, one of the most recognizable patterns in the sky. From there, glance up and to the left. The red-orange star you see glowing like an ember against the darkness is Betelgeuse. Down and to the right, you'll spot Rigel, a brilliant blue-white star marking Orion's foot. The contrast between them is striking. Rigel burns cold and bright, a young star barely 10 million years old, while Betelgeuse glows warm and deep, like a coal pulled from a fire that's been burning for eons. That red glow isn't just pretty, it's a warning sign written in light. In the language of stars, color reveals temperature and temperature reveals age. Blue stars are young and scorching hot, burning at 50,000 degrees Celsius or more, racing through their fuel in just a few million years. Yellow stars, like our sun, sit around 5,500 degrees, stable and middle-aged, with billions of years left to burn. But red stars are cool only 3,500 degrees at the surface. And when a massive star cools down and turns red, it means one thing: it's nearing the end of its life. Betelgeuse sits 650 light-years away. That's far enough that the light reaching your eyes tonight left the star in the year 1374 during the Middle Ages, when the Black Death had just finished ravaging Europe, when the Ming dynasty was rising in China, when the Renaissance hadn't yet begun. The Betelgeuse you see is a ghost, a memory of a star that existed more than 6 centuries ago. When you look at Betelgeuse, you're not seeing it as it is now. You're seeing it as it was before Columbus sailed to the Americas, before the printing press was invented, before Shakespeare was born. And here's where things get strange. Most stars shine with steady, predictable brightness. They're constant, reliable, unchanging over human lifetimes. But Betelgeuse doesn't follow that pattern. It brightens and dims in cycles, sometimes outshining, even Rigel, sometimes fading so much that it drops out of the top 10 brightest stars entirely. Astronomers have tracked these changes for over a century, recording the star's brightness night after night, year after year, watching Betelgeuse pulse like a heartbeat, slow, irregular, impossible to pin down with perfect accuracy. The variability isn't subtle. On some nights, Betelgeuse is bright enough to rival Sirius, the brightest star in the sky. On others, it dims to the point where casual observers might not even notice it. The range is dramatic enough that ancient astronomers noted it, recording in their star catalogues that Betelgeuse was variable long before they understood what that meant. Consider this: every photon of light that hits your retina when you look at Betelgeuse traveled for 650 years through the emptiness of space, carrying information about a star that may have already exploded by the time you're hearing this. The star could have gone supernova in the year 1700 or 1800 or 1900, and we wouldn't know yet. The light from that explosion would still be racing toward us, crossing trillions of miles of void invisible until it finally arrives. We could be living in the last century, or the last decade, or the last year before Betelgeuse's death becomes visible to us. But if Betelgeuse were closer, say the same distance from Earth as our Sun, a mere 93 million miles, we wouldn't be here to see it. We wouldn't exist. The sheer brightness would incinerate our planet in seconds, stripping away the atmosphere, boiling the oceans, melting the crust. Betelgeuse outshines the Sun by 100,000 times. It radiates more energy in a single day than the Sun does in 3 months. It's not just a star. It's a furnace on a scale that our Sun, for all its power, can't even approach. Among the 10 brightest stars visible from Earth, Sirius Canopus, Arcturus, Vega, Capella, Rigel, Procyon, Achernar, and Altair Betelgeuse is the only one that glows red. The rest are blue-white or yellow-white stars still in their prime or just beginning their decline. Betelgeuse stands out because it's already deep into its death spiral, already burning through the last reserves of fuel in its core. That red color is the visual signature of a star running out of time, a countdown visible from 650 light-years away. For backyard stargazers and ancient navigators alike, Betelgeuse has always been a landmark, a guidepost in the winter sky. But for astronomers, it's become something else entirely, a laboratory for studying what happens when massive stars die. And in the last few years, that laboratory has started producing results no one expected, revealing behaviors that challenge our understanding of how stars work. What makes a star burn this bright and glow this red? To understand that, we need to look at what Betelgeuse actually is, not just a point of light in Orion's shoulder, but a physical object with size, mass, and structure. We need to understand why it's become so impossibly terrifyingly large. If you could replace our Sun with Betelgeuse, the surface of the star would stretch past the orbit of Jupiter. Mercury, Venus, Earth, Mars, all of them would be swallowed whole, vaporized inside the star's outer layers, before they even reached what we'd call the surface. Even Jupiter, the giant of our solar system, a planet so large you could fit 1,300 Earths inside it, would be engulfed. The star would fill the inner solar system like water filling a glass, drowning the rocky planets, and reaching outward until it touched the gas giants. Betelgeuse is about 1,000 times wider than the Sunday. Let that sink in for a moment. If the Sun were the size of a basketball, Betelgeuse would be as wide as a professional basketball arena. If the Sun were a marble, Betelgeuse would be a beach ball 3 feet across. The scale is almost incomprehensible. But here's the strange part: despite being so enormous, Betelgeuse only weighs about 20 times more than the Sunday. It's like taking a balloon and inflating it to 1,000 times its original size without adding any air. The material stretches thinner and thinner, spreading out over a vast volume. Stretch the Sun out to 1,000 times its size without adding much mass, and the density drops catastrophically. The outer layers of Betelgeuse are thinner than the air you're breathing right now, less dense than the vacuum inside a light bulb, less dense than the upper atmosphere of Earth at 100 miles altitude. If you could somehow stand on the surface of Betelgeuse, if such a thing even existed, you'd barely feel anything around you. There would be no ground beneath your feet, no clear boundary between star and space. It would be like floating in a warm, glowing fog that gradually thickened as you descended, growing hotter and denser the deeper you went, until eventually the pressure crushed you and the heat vaporized your atoms. But at the edge, where the star meets space, you could pass through the outer layers with your hand and feel almost nothing. Compare that to our Sun, which is dense and compact, a tightly bound sphere of plasma held together by gravity. The Sun's core is packed so tightly that a teaspoon of material from its center would weigh about 200 grams, roughly the weight of a baseball. At that density, the core generates enough pressure and heat to fuse hydrogen into helium, releasing the energy that makes the Sun shine. Betelgeuse's outer atmosphere, by contrast, is so thin that you could scoop up a cubic meter of it, a space the size of a washing machine, and the material would weigh less than a feather. It's barely there, a ghost of a star held together by gravity alone. Stars aren't supposed to be this way. They start their lives small, dense, and stable, burning hydrogen in their cores with ruthless efficiency. Our Sun, for example, has been burning hydrogen in its core for about 4.6 billion years, converting 600 million tons of hydrogen into helium every single second. It'll keep doing that for another 5 billion years, maintaining roughly the same size and temperature throughout. It's a middle-aged star halfway through its life, and it's been the same size for most of its existence. Stability is the norm for stars like the Sunday. But massive stars born with more than 10 times the Sun's mass, don't get to be stable. They burn through their fuel at a reckless pace, fusing hydrogen into helium hundreds or thousands of times faster than the Sun does. They're profligate, wasteful living, fast and dying young. A star like Betelgeuse, born with 20 times the Sun's mass, will burn through its entire hydrogen supply in just 10 million years. Compare that to the Sun's 10 billion year lifespan. Betelgeuse burns 1,000 times faster, and it pays the price. Betelgeuse formed about 10 million years ago, give or take a few million. That sounds like a long time, longer than human civilization, longer than the existence of our species. But in cosmic terms, it's nothing. Dinosaurs roamed Earth for 165 million years. Betelgeuse's entire life from birth to death will be shorter than the span between the rise and fall of the dinosaurs. And it's already in its final stage, already dying. When a massive star runs out of hydrogen in its core, it doesn't just shut down like a car running out of gas. Instead, the core contracts under its own gravity, and the temperature inside spikes. The contraction releases gravitational energy, and that energy heats the core until it's hot enough to ignite helium, fusing it into carbon and oxygen. But the outer layers of the star, starved of the outward pressure that kept them in place, begin to expand. With no hydrogen burning in the core to push them outward, the outer layers drift away from the center, swelling like a balloon. The star grows larger, but cooler. It becomes a red supergiant, growing hundreds or even thousands of times its original size. Betelgeuse is in that stage now. Its core is a dense, roiling furnace, burning helium and heavier elements in concentric shells like the layers of an onion. Hydrogen burns in a shell around the core, fusing into helium. Deeper inside, helium burns, fusing into carbon and oxygen. Below that, in the very center, carbon and oxygen fuse into neon and magnesium. Each layer burns at a different temperature, each one feeding energy outward, but the balance is precarious. The star is held together by nothing more than the tension between gravity pulling inward and heat pushing outward. If the balance shifts even slightly, the star could collapse, or it could explode. Surrounding that core is a vast shell of gas so large that if you flew a spaceship at the speed of light, it would take over an hour to cross from one side of the star to the other. Light moving at 300,000 kilometers per second, fast enough to circle the Earth 7 times in 1 second, would need an hour to cross Betelgeuse. Our Sun, by comparison, takes just 2.3 seconds to cross at light speed. Betelgeuse isn't just bigger than the Sunday. It's bigger than our entire inner solar system, a bubble of glowing gas held together by gravity and nothing else. The surface temperature of Betelgeuse sits at around 3,500 degrees Celsius. That's cooler than the Sun's surface by 2,000 degrees. The Sun's surface temperature is about 5,500 degrees hot enough to glow yellow-white. Betelgeuse, cooler by comparison, glows red-orange, and that difference in temperature is why it glows red instead of yellow. Hot things glow blue or white. Cool things, at least by stellar standards, glow red. It's the same reason a piece of metal glows red when heated to 1,000 degrees but glows white when heated to 3,000. But cool is relative. 3,000 to 500 degrees is still hot enough to vaporize steel in an instant, hot enough to melt tungsten, the metal with the highest melting point known to science, used in light bulb filaments because nothing else can withstand the heat. Hot enough that if Betelgeuse were close enough to touch, you'd be atomized long before you felt the heat, your molecules torn apart by the sheer intensity of the thermal radiation. The star's outer layers are so diffuse that they barely qualify as matter. The density there is lower than the best laboratory vacuum chambers on Earth, lower than the space between planets in our solar system. And yet, because the star is so vast, because it stretches over such an enormous volume, those thin outer layers still contain more mass than the entire planet Jupiter. It's a paradox, a star made mostly of empty space, but still weighing 20 times more than the Sunday. The energy pouring out of Betelgeuse is staggering, almost incomprehensible. Every second it radiates 100,000 times more energy than the Sunday. To put that in perspective, if you could capture all the energy Betelgeuse emits in 1 second, just 1 second, it would be enough to power human civilization at current consumption levels for millions of years. All the electricity, all the fuel, all the energy we use for millions of years from 1 second of Betelgeuse's output. If Betelgeuse were the same distance from Earth as the Sun, 93 million miles close enough to warm our planet and keep us alive, the heat would melt, rock boil, oceans and strip away our atmosphere in minutes. The Earth would be a cinder, a molten ball of lava, uninhabitable. We'd be incinerated before we even realized what was happening. But Betelgeuse isn't stable. Stars like it don't die quietly, don't fade gently into the night. They pulse, they flicker. They eject enormous bubbles of gas into space, shedding mass like a snake shedding skin. The outer layers heave and churn, driven by convection currents as large as the orbit of Mars. Imagine bubbles of hot gas, each one bigger than Earth, rising from deep inside the star to the surface, cooling and sinking back down. That's what's happening inside Betelgeuse. Every day a roiling chaos of heat and motion. And eventually, when the core runs out of fuel entirely, when every last atom of fusible material has been burned, the star will explode in a supernova, a blast so bright it can outshine an entire galaxy for weeks. The core will collapse into a neutron star or black hole. The outer layers will be flung into space at tens of thousands of kilometers per second. And for a brief moment, Betelgeuse will release more energy than it has emitted over its entire 10 million year lifetime. Pause on this. Betelgeuse is a star that weighs 20 times more than the Sun, but it's stretched so thin that its outer layers are nearly empty space. It's a bubble of light and heat held together by gravity alone, burning through the last stages of its fuel at a rate that would drain our Sun in a few thousand years. It's a giant on the edge of collapse, radiating more energy in a single day than our Sun does in 3 months. It's a star that defies intuition, a star that shouldn't exist but does, a star that's already dying. And that brings us back to late 2019, when Betelgeuse did something no one had ever seen a red supergiant do before. It dimmed so drastically, so suddenly, that the world started asking, is this the end? Is Betelgeuse about to explode? In October 2019, astronomers monitoring Betelgeuse noticed something odd. The star was getting dimmer. Not just a little dimmer, significantly dimmer than it had been in over a century of observations. By December, the star had lost about 40% of its normal brightness. By February 2020, it had dropped by more than 60%, fading to levels never recorded before. For a star that had been pulsing predictably for over 100 years, this was unprecedented. This was wrong. Amateur astronomers could see the change with their own eyes, without telescopes, without instruments. Betelgeuse, usually one of the brightest stars in Orion, had faded to the point where it was barely noticeable. Dim enough that some observers reported having trouble finding it in the sky. In the astronomy community, speculation ran wild. Online forums lit up with theories. News outlets started running stories. Some wondered if Betelgeuse was about to go supernova, if we were witnessing the final days of a dying star. After all, dimming is one of the potential warning signs. If the core of a massive star collapses, the outer layers can briefly darken before the explosion tears the star apart. But supernovae don't just dim, they explode. They brighten catastrophically, suddenly going from a normal star to a point of light brighter than billions of stars combined. And Betelgeuse didn't explode. Instead, by April 2020, it started brightening again. Slowly at first, then more rapidly. By mid-year, it was back to its normal luminosity, glowing as brightly as it had before. The panic subsided, but the mystery remained. What had happened? What could cause a star to dim by 60% and then recover? The answer came in 2021, when a team of astronomers led by Miguel Montages at the European Southern Observatory published their findings in the journal Nature. Using the Sphere instrument on the Very Large Telescope in Chile, one of the most advanced astronomical instruments on Earth, they had captured images of Betelgeuse's surface before, during, and after the dimming event. What they saw was extraordinary, unprecedented, a glimpse into a process that had only been theorized before. Betelgeuse had ejected a massive bubble of plasma from its surface. The bubble was enormous, several times the mass of the Moon, a clump of gas weighing as much as a small planet. It rose from the star's southern hemisphere, driven by convection currents deep inside the star. As it rose, it cooled, and when hot gas cools, in the vacuum of space, it condenses. The carbon, silicon, and other heavy elements in the gas formed dust particles, creating a cloud so dense it blocked a significant portion of the star's light. From Earth, 650 light-years away, it looked like Betelgeuse was dimming, but the star itself hadn't changed. It was still shining just as brightly as before. It was just hidden behind its own debris, like a streetlight obscured by fog, like the sun disappearing behind a cloud. The light was still there, but we couldn't see it. The cloud formed on the southern hemisphere of Betelgeuse, covering roughly a quarter of the star's visible surface when viewed from Earth. For months, that dust cloud lingered, drifting slowly outward, scattering and absorbing light. The cloud was cold, only about 1000 degrees Celsius, cold enough for solid particles to exist. And those particles, each one smaller than a grain of sand, blocked the light like tiny shields dimming the star. Eventually, the cloud dispersed. The dust particles drifted apart, spreading out over a larger volume, thinning until they were too diffuse to block much light, and Betelgeuse emerged from behind the veil as bright as ever, as if nothing had happened. Scientists started calling it the Great Dimming. Some referred to it as a stellar sneeze, a convulsive expulsion of material that the star had built up in its outer layers. The comparison is apt. When you sneeze, you expel droplets of mucus and saliva that briefly cloud the air in front of your face. Betelgeuse did the same thing, except the droplets were clumps of plasma, weighing billions of tons, and the cloud was large enough to engulf the entire inner solar system. But this wasn't a one-time fluke, wasn't an anomaly that happened once and never again. Betelgeuse has been ejecting material into space for thousands of years, possibly for millions of years. The star is surrounded by shells of gas and dust remnants of previous eruptions. Infrared telescopes can see them glowing faintly in the cold of space, concentric rings spreading outward like ripples on a pond. Each ring represents a past ejection, a moment when the star coughed up material and sent it drifting into the void. Red supergiants like Betelgeuse lose mass, constantly shedding material like a dog shedding fur. Every year, Betelgeuse sheds material equivalent to the mass of Earth, 6 trillion kilograms of gas blown into space by radiation pressure and stellar winds. Over its lifetime, it's lost several solar masses worth of gas, puffing it out into the surrounding space, creating a nebula of ejected material that stretches for light years around the star. That mass loss is part of the dying process. The star is shedding its outer layers, exposing the hotter, denser material below, preparing for the eventual collapse of the core. But the Great Dimming was different. It wasn't gradual mass loss. It wasn't the slow, steady shedding of gas that red supergiants do all the time. The bubble was so large that if you placed it next to Earth, it would dwarf our planet entirely, filling the sky from horizon to horizon. And the dust that formed from that plasma weighed several times more than the Moon, a cloud of particles dense enough to block 60% of the star's light. The mechanism behind the ejection is still being studied, still being debated in scientific journals and conferences. But the leading theory involves convection, the same process that creates weather on Earth. Deep inside Betelgeuse, massive convection cells, bubbles of hot gas rising from the core churn through the star's interior. When one of these bubbles reaches the surface, it can punch through the star's outer layers, flinging material into space. It's like a pot of boiling water on a stove where bubbles of steam rise to the surface and burst. Except the pot is 1,000 times wider than the sun, and the bubbles are the size of planets. One particular convection cell, larger and hotter than usual, rose to the surface in late 2019. When it broke through, it launched a bubble of plasma outward with enough energy to escape the star's gravity. The plasma cooled rapidly, dropping from tens of thousands of degrees to a few thousand in a matter of days. And when it cooled below a critical threshold around 1500 degrees Celsius, the heavy elements in the gas condensed into solid particles. Carbon formed graphite. Silicon formed silicates. The plasma became dust. That dust cloud lingered for months, slowly spreading out, gradually thinning. Infrared observations showed the cloud drifting away from the star, carried by radiation pressure and the star's own rotation. By mid-2020, the cloud had dispersed enough that Betelgeuse's light could shine through again. The great dimming was over. For astronomers, the event was a gift, an unexpected opportunity to witness a process that had only been theorized. It gave them a rare close-up look at how red supergiants eject material into space. It confirmed that these stars don't just slowly leak gas, they can violently expel it in massive bursts, creating clouds of dust that block their own light. It showed that Betelgeuse is far more dynamic than anyone had realized, far more active, far more chaotic. But the great dimming did something else, something unexpected. It changed the star's rhythm. For over a century, Betelgeuse had pulsed with a primary cycle of about 400 days, a rhythm so consistent that astronomers used it to predict the star's brightness months in advance. That cycle was Betelgeuse's heartbeat, a steady drum marking the passage of time. But after the great dimming, that 400-day cycle vanished. And in its place, a new rhythm emerged, one that no one had expected, one that suggested the star had been fundamentally altered by the violence of the ejection. Stars pulse. It's one of the fundamental behaviors of red supergiants, a consequence of the physics of heat and pressure deep inside the star. As the outer layers expand, they cool, and the star dims. As they contract, they heat up, and the star brightens. This cycle repeats over and over, driven by oscillations in the star's interior, a rhythmic expansion and contraction that can last for hundreds or thousands of days. For Betelgeuse, that pulse had been remarkably stable for over a century. The primary cycle was about 400 days, roughly 13 months. Astronomers tracked it for decades, recording the star's brightness, night after night, year after year, building a database of observations that stretched back to the 1800s. The 400-day rhythm was Betelgeuse's heartbeat, a steady drum marking the passage of time as reliable as the ticking of a clock. But after the great dimming, the heartbeat stopped. When Betelgeuse brightened again in mid-2020, astronomers expected the 400-day cycle to resume. They expected the star to return to normal, to slip back into the rhythm it had maintained for over a century. It didn't. Instead, a new rhythm appeared, a pulse of about 200 days, roughly half the original period. The star was beating twice as fast, like a heart that had been shocked into a new rhythm. This wasn't just a temporary change, wasn't a brief fluctuation that would fade after a few cycles. The 200-day cycle persisted through 2021, 2022, and 2023. It's still going. Betelgeuse's rhythm has fundamentally shifted, and no one is entirely sure why. The star that had pulsed at 400 days for over a century was now pulsing at 200 days, and the change showed no signs of reversing. The most likely explanation involves something called overtone pulsation, a phenomenon predicted by theoretical models but rarely observed in real stars. To understand this, think of a guitar string. When you pluck a string, it vibrates at a fundamental frequency, the lowest pitch it can produce, determined by the string's length, tension, and mass. But the string also vibrates at higher frequencies, called overtones or harmonics. These overtones are faster, higher-pitched vibrations layered on top of the fundamental tone. If you pluck the string hard enough, or in just the right way, you can make it vibrate primarily at an overtone frequency instead of the fundamental. Stars can do something similar. The outer layers of a star vibrate at a fundamental frequency, the primary pulsation cycle. But under certain conditions, the star can switch to an overtone mode, vibrating at a higher frequency, pulsing faster. In Betelgeuse's case, the great dimming may have jolted the star so hard that it knocked the pulsation into a higher overtone mode. The violent ejection of plasma, the sudden loss of mass, the disruption of the convection cells, all of this may have been enough to shift the star's pulsation from the fundamental mode to the first overtone. It's as if someone struck the star like a bell, and instead of ringing at its usual deep tone, it started ringing at a higher pitch. The bell is the same. The structure hasn't changed, but the way it vibrates, the way it responds to being struck, has shifted to a new mode. Theoretical models of stellar pulsation predicted that this could happen, that red supergiants, under certain conditions, could switch from fundamental mode to overtone mode. But no one had ever observed it in a real star before. Betelgeuse is the first red supergiant known to have switched pulsation modes in real time, the first star where we've watched the rhythm change before our eyes. And the fact that it happened after such a violent event, the ejection of a massive bubble of plasma, suggests that the two phenomena are connected, that the Great Dimming didn't just obscure Betelgeuse's light, but actually changed the star's internal structure. The Great Dimming didn't just affect the surface. It disrupted the star's interior. The convection cells that drive the pulsation were thrown into chaos. The balance between heat and pressure shifted. The outer layers, which had been oscillating in a stable pattern for over a century, were suddenly pushed into a new configuration. And when the star settled back into equilibrium, it settled into a new rhythm, a new mode of vibration that was faster, more energetic, more intense. But there's another possibility, one that's more troubling, more urgent. Some researchers have suggested that the change in pulsation could be a sign that Betelgeuse is evolving, that the core is running out of fuel faster than expected, that the star is transitioning to a new phase of its life. If that's true, then the 200-day pulse might not be temporary. It might be the new normal, a signal that Betelgeuse is accelerating toward its final collapse. In stellar evolution, the pulsation pattern of a star can change as the core exhausts different fuels. When a star is burning hydrogen in a shell around the core, it pulsates in one way. When it transitions to burning helium, the pulsation changes. When it starts burning carbon, it changes again. Each phase of fusion produces a different pattern of oscillation, a different rhythm. If Betelgeuse has transitioned to burning a new fuel, if it's moved from helium to carbon or from carbon to neon, then the change in pulsation could be a sign that the star is closer to its death than we thought. The shift in rhythm also complicates efforts to predict when Betelgeuse will go supernova. Before the Great Dimming, astronomers used the 400-day cycle to model the star's internal structure. They knew how much energy the star was radiating, how fast it was losing mass, how quickly it was burning through its fuel. Those models gave estimates of how much time Betelgeuse had left: decades, centuries, tens of thousands of years, depending on the assumptions. But with the rhythm changed, those models no longer apply. The star is operating under a new set of rules, pulsating in a way that doesn't fit the old predictions. We're back to square one, trying to understand what's happening inside the star based on limited observations and incomplete data. Consider this. Betelgeuse is a star with a mass 20 times greater than the Sun, a size so vast it could swallow Jupiter, and an internal furnace burning through the last stages of nuclear fusion. And after a single violent event, a sneeze that ejected material, the mass of several moons, its entire pulsation pattern changed. The star is not just dying, it's evolving in real time, adapting to the chaos unfolding inside it, shifting from one mode of vibration to another in response to forces we barely understand. And yet, even as astronomers worked to understand the new rhythm, another mystery was quietly lurking in the data, a mystery that had been there all along, hidden in plain sight for over 40 years. It took decades to notice, but when scientists finally pieced it together in 2024, it revealed something no one had imagined. Betelgeuse wasn't alone. There was another star there, orbiting through the giant's atmosphere, stirring waves in the gas, creating a cycle that had puzzled astronomers since the 1980s. For over 40 years, astronomers had known about another cycle in Betelgeuse's brightness, a long, slow oscillation that repeated every 2,100 days, or about 6 years. Unlike the primary pulse, which was clearly driven by the star's expansion and contraction, this longer cycle was harder to explain. It was subtle, a gentle rise and fall in brightness superimposed on the more dramatic 400-day pulse. Some thought it might be caused by giant convection cells slowly rotating across the star's surface, like sunspots drifting across the Sunday. Others suggested it could be related to magnetic fields, threading through the star's atmosphere, or internal waves, propagating through the layers of gas. But in December 2024, a team led by astrophysicist Jared Goldberg at the Flatiron Institute announced a stunning discovery that changed everything. The 6-year cycle wasn't caused by Betelgeuse itself. It was caused by another star. Using data from the ALMA telescope array in Chile, a collection of 66 radio dishes spread across the Atacama Desert, working together to create a telescope the size of a city, Goldberg's team detected a small companion star, orbiting Betelgeuse at a distance roughly equal to the distance between the Sun and Earth. The companion, which they nicknamed Suwa, a Japanese word meaning bracelet, suggesting something that in circles is much smaller than Betelgeuse, with a mass only about 1.5 times that of the Sunday. It's an ordinary star by most measures, nothing special. But its orbit brings it perilously close to the red giant's outer atmosphere, close enough that the two stars aren't just orbiting each other, they're interacting. Suwa doesn't orbit outside Betelgeuse's atmosphere, safely separated from the giant's outer layers. It orbits through it. Every 6 years, Suwa plunges through the diffuse outer layers of Betelgeuse, carving a path through the gas like a speedboat, cutting through water like a comet streaking through Earth's atmosphere. It stirs up waves in the gas compressors. The material in front of it drags some of it along in its wake. Those waves alter the density and temperature of the gas, which in turn changes how much light the star emits. From Earth, 650 light-years away, we see that change as a slow oscillation in brightness. The 2,100-day cycle that had puzzled astronomers for decades. The discovery of Suwa solved a long-standing mystery, answered a question that had been nagging at astronomers since the 1980s. But it also raised new questions, opened new doors, suggested that Betelgeuse's history was more complicated than anyone had realized. How did a smaller star end up in such a tight orbit around a red supergiant? And how has it survived this long skimming through the outer layers of a star that's 1,000 times larger? The most likely explanation is that Suwa was part of a binary system with Betelgeuse from the beginning, that the two stars formed together in the same molecular cloud 10 million years ago. When two stars form close together, they orbit each other, bound by gravity, locked in an eternal dance. As one star ages and expands into a red supergiant, it can engulf part of the companion star's orbit. In Betelgeuse's case, the star expanded so much, grew so large, that Suwa's orbit now passes through its outer atmosphere, dipping into the star's outermost layers every 6 years. But Suwa hasn't been torn apart, hasn't been destroyed by the passage. The outer layers of Betelgeuse are so thin, less dense than the air you're breathing, less dense than the vacuum inside a spacecraft, that Suwa can pass through them without suffering catastrophic damage. It's like flying a plane through a cloud. The cloud is there, you can see it, it's made of water droplets and ice crystals. But it's so diffuse, so spread out, that the plane passes through without slowing down, without even noticing the resistance. Suwa does the same thing, plunging through Betelgeuse's atmosphere at tens of kilometers per second, encountering gas that's barely there. However, Suwa's passage isn't entirely harmless. Every time it plunges through Betelgeuse's atmosphere, it compresses the gas in front of it, creating a shock wave, a region of higher pressure and temperature that propagates outward like the sonic boom from a supersonic jet. That shock wave heats the gas, causing it to glow brighter. At the same time, Suwa drags some of the gas along with it, creating a wake, a trail of disturbed material that takes months to settle back down, like the wake behind a boat that takes minutes to smooth out. The waves generated by Suwa propagate through Betelgeuse's outer layers, spreading across the star's surface like ripples on a pond. Those ripples affect the star's brightness, producing the 6-year cycle that astronomers had been tracking for decades. It's a bit like watching the surface of a pond on a calm day. Most of the time, the water is still, but every so often, a stone drops into it, sending ripples spreading outward, disturbing the surface, creating patterns that fade slowly as the energy dissipates. Suwa is that stone dropping into Betelgeuse's atmosphere every 6 years. The discovery of Suwa in 2024 was a reminder that even well-studied stars can hold secrets, can hide companions, can surprise us with revelations that change our understanding. Betelgeuse has been observed for centuries. It's one of the most famous stars in the sky, one of the most studied, one of the most photographed. And yet, until recently, no one knew it had a companion. The star we thought we understood turned out to be hiding something fundamental, something that had been there all along, creating a cycle visible in the data but unexplained until now. But Suwa might not be the only secret Betelgeuse is keeping. There are hints, subtle anomalies in the star's rotation and chemical composition that suggest something else happened in Betelgeuse's past, something more violent than the arrival of a companion star. Something that might explain why Betelgeuse is the way it is today, why it spins faster than it should, why its atmosphere contains elements that shouldn't be there. Betelgeuse spins, All stars spin. It's a natural consequence of their formation, a leftover from the rotation of the gas cloud that collapsed to form the star. The sun spins, completing one rotation every 25 days at its equator. Betelgeuse should spin too, but slowly, very slowly. For a red supergiant, rotation is usually glacial. When a star expands, its rotation slows down, just like a figure skater extending their arms to decelerate a spin or a spinning top, gradually winding down as friction takes its toll. It's a consequence of the conservation of angular momentum. As the star grows larger, the same amount of rotational energy gets spread out over a larger volume and the rotation rate drops. Betelgeuse should be rotating at about 1 kilometer per second or less at its equator, a leisurely pace for a star so large. But measurements taken over the last 2 decades, using techniques that track the motion of gas across the star's surface, show that Betelgeuse's equator is moving at about 5 kilometers per second. That's 5 times faster than expected, 5 times faster than a star this size should be rotating. And it's a clue, a piece of evidence that something unusual happened in Betelgeuse's past, something that spun it up, injected angular momentum, gave it a kick. The other clue comes from the star's atmosphere, from the light it emits. Spectroscopic analysis studying the wavelengths of light Betelgeuse emits to determine its chemical composition has revealed something odd, something that doesn't fit the standard model of stellar evolution. The surface of Betelgeuse contains more nitrogen than it should. Nitrogen is produced deep inside a star's core through a process called the CNO cycle, where carbon, nitrogen, and oxygen are cycled through nuclear reactions, fusing hydrogen into helium while creating nitrogen as a byproduct. Under normal circumstances, nitrogen stays locked in the core, buried deep inside the star, never rising to the surface. The convection zones in a star mix the outer layers, but they don't usually reach deep enough to dredge up material from the core. But Betelgeuse's surface has elevated nitrogen levels higher than what you'd expect from a star of its age and mass. And that suggests the star's interior has been mixed. Something has dredged up material from deep inside and brought it to the surface, stirring the star like a spoon, stirring a pot of soup. There are 2 ways this can happen. One is through convection. As gas rises and falls inside the star, it can carry material from deeper layers to the surface. But convection alone doesn't usually produce the level of mixing seen in Betelgeuse. The convection zones in a red supergiant are powerful, but they're not powerful enough to reach all the way down to the core and pull nitrogen-rich material up to the surface. There's a boundary, a region where convection stops and radiative transport takes over. The other explanation is more dramatic, more violent. Betelgeuse may have merged with another star. Stellar mergers happen more often than you might think. When 2 stars orbit each other closely, they can lose energy through gravitational interactions, through tidal forces that sap their orbital energy and convert it into heat. Over time, the orbit shrinks. The stars spiral inward, getting closer and closer until they collide. The collision doesn't destroy the stars, it merges them. The smaller star is absorbed into the larger one, torn apart by tidal forces, its core mixed into the outer layers of the larger star. And the resulting object is a single, more massive star born from the fusion of 2. But the merger leaves behind evidence, leaves scars, leaves traces that can be detected if you know where to look. When 2 stars collide, the smaller star's core is torn apart and mixed into the larger star's outer layers. That mixing can bring nitrogen-rich material to the surface material that was once buried deep inside one of the stars. The collision also transfers angular momentum, causing the merged star to spin faster. It's like 2 ice skaters colliding and spinning together. The combined system rotates faster than either skater alone. Betelgeuse shows both of these signs: elevated nitrogen and fast rotation. And that's led some astronomers to propose that Betelgeuse isn't a single star that simply evolved into a red supergiant. Instead, it might be the product of a merger, 2 stars that collided and fused together millions of years ago, creating a single, more massive star with unusual properties. If that's true, then Betelgeuse's mass may be higher than we think. Instead of being a 20 solar mass star, born as a single object, it could be a 30 solar mass star. The result of combining 2 smaller stars, one with 15 solar masses, the other with 15 merging to create a Titan 25 cross-group giant, and a more massive star burns through its fuel faster. It dies younger. it explodes sooner. If Betelgeuse is the product of a merger, it might be closer to the end than current models suggest. The merger hypothesis is still debated, still controversial. Not all astronomers agree that the evidence is strong enough to conclude that Betelgeuse merged with another star. Some argue that the elevated nitrogen could be explained by other processes like rotational mixing or unusual convection patterns. Others point out that the rotation rate, while high, isn't so extreme that it requires a merger to explain. But the anomalies are real. Betelgeuse spins too fast. It has too much nitrogen, and those anomalies demand an explanation, demand a story that fits the facts. One possibility is that Betelgeuse had a close companion, not Suwa, but a third star larger and closer that spiraled inward over millions of years. The companion transferred angular momentum to Betelgeuse, spinning it up, making it rotate faster. Eventually, the companion was consumed, absorbed into Betelgeuse's outer layers, torn apart by tidal forces, its core mixed into the giant's atmosphere. The merger left no trace except for the elevated nitrogen, and the faster rotation subtle clues that Betelgeuse's history is more violent than it appears. If Betelgeuse did merge with another star, it would have happened long ago, perhaps 5 or 10 million years ago, early in the red supergiant phase, before the star had expanded to its current size. By now, the evidence has been partially erased by the star's ongoing mass loss and convection. Every year, Betelgeuse sheds material equivalent to the mass of Earth, blowing it into space. Over millions of years, that mass loss has stripped away much of the outer layers, removing some of the nitrogen-rich material, erasing some of the chemical signatures. But the signs remain faint but detectable, like fingerprints on a crime scene that's been cleaned but not thoroughly. The presence of Suwa adds another layer to the story, suggests that Betelgeuse's history is even more complex than we thought. If Betelgeuse once had two companions, one that merged with it and one that survived it, suggests the system was originally a triple star system. 3 stars born together, orbiting each other in a gravitational dance. Triple stars are common in the universe, more common than single stars like the Sunday, but they're inherently unstable. Over time, gravitational interactions can cause one star to spiral inward while another gets flung outward, or one star merges while another survives in a distant orbit. Suwa may be the survivor of such an interaction, left in a close orbit around the merged remnant, the last witness to a collision that happened millions of years ago. This isn't just speculation, isn't just storytelling. Recent simulations of stellar evolution have shown that mergers can produce stars that look exactly like Betelgeuse, fast-rotating, nitrogen-rich red supergiants with unusual pulsation patterns and high mass loss rates. The models match the observations. The theory fits the data, and that makes the merger hypothesis increasingly plausible, increasingly likely, increasingly hard to dismiss. Consider this. Betelgeuse may not be what it seems. The star we see today, a red supergiant nearing the end of its life, pulsing erratically, shedding mass into space, could be the product of a cosmic collision, 2 stars smashed together into one millions of years ago. The nitrogen in its atmosphere is the ghost of the devoured star brought to the surface by the violence of the merger, a chemical signature of a star that no longer exists. The fast rotation is the echo of that collision, still spinning, Betelgeuse faster than it should, a leftover momentum from the impact. And if that's true, then the question isn't just when will Betelgeuse explode, it's what kind of explosion will it be, because a star born from a merger might not die the way a normal star does. It might have more mass than we think. It might burn through its fuel faster. It might explode sooner, brighter, more violently. The merger might have changed everything, set Betelgeuse on a different path, a shorter path, a path that ends in an explosion that's closer than we expect. The question everyone wants answered, the question that drives headlines and captures imaginations: when will Betelgeuse go supernova? The honest answer, the answer that scientists give when pressed, is no one knows. Not with any certainty, not with any precision. Supernovae are notoriously difficult to predict. The final stages of a massive star's life depend on a complex interplay of nuclear fusion, convection, mass loss, rotation, magnetic fields, and gravity. Small changes in any of these factors can shift the timeline by thousands of years, maybe tens of thousands. And because we're observing Betelgeuse from 650 light-years away, seeing it as it was in the 14th century, we have no idea what the star is doing right now in real time. It could be stable, it could be flickering, it could be on the verge of collapse, or it could have already exploded, and the light from that explosion is racing toward us at 300,000 kilometers per second, less than a century away from arrival. But astronomers have tried to estimate. They've built models, run simulations, analyzed the data, made educated guesses based on the best understanding of stellar physics. And the estimates vary, wildly spanning a range that's almost comically broad. In 2023, a team led by Hideyuki Sayo at Tohoku University in Japan published a controversial paper suggesting that Betelgeuse could explode within a few hundred years, perhaps even sooner. Their argument was based on the star's pulsation patterns, on the way it oscillates and the frequencies of those oscillations. By analyzing how Betelgeuse vibrates, they estimated the density and temperature of its outer layers and the structure of its interior. Their models suggested that the core was already burning carbon, one of the final stages before collapse. Carbon fusion is the second to last step in the life of a massive star. After carbon comes neon, oxygen, silicon, and finally iron. Once the core fills with iron, fusion stops, and the star has minutes to live. If Sayo's team is right, if Betelgeuse is already burning carbon, then it's running out of time. Carbon burns fast, much faster than helium, much faster than hydrogen. A 20 solar mass star can burn carbon in its core for only a few hundred years before moving on to the next stage. And once it starts burning silicon, it has days, maybe weeks, and then it's over. But other astronomers disagree strongly and publicly. The majority view is that Betelgeuse still has tens of thousands of years left, perhaps 100,000 years, maybe more. These estimates are based on models of stellar evolution that track how massive stars burn through their fuel over time, from hydrogen to helium to carbon to neon, step by step, stage by stage. According to these models, Betelgeuse is still burning helium in its core, not carbon. It's not yet in the final countdown. It's still in the middle stages of its death, not the final act. The truth is probably somewhere in between, somewhere in the vast uncertainty between a few hundred years and 100,000 years. Betelgeuse is clearly in the late stages of its life. It's a red supergiant shedding mass at a prodigious rate, pulsating erratically, showing signs of internal instability. But predicting exactly when the core will collapse is like predicting when a dam will break. You know it's under stress. You know it's weakening. You can see the cracks forming. But you don't know when the final failure will occur, when the last support will give way, when the structure will finally crumble. One thing is certain: when Betelgeuse does explode, it will be spectacular. It will be one of the most dramatic astronomical events in human history, visible to the naked eye for months, talked about for generations. A supernova occurs when the core of a massive star runs out of fuel. For most of the star's life, nuclear fusion in the core produces an outward pressure that balances the inward pull of gravity. Hydrogen fuses into helium, releasing energy. Helium fuses into carbon and oxygen, releasing energy. Carbon fuses into neon, oxygen, into silicon, into iron. At each stage, fusion produces heat and pressure, pushing outward, holding the star up against its own weight. But when the core exhausts its fuel, when every last atom of fusible material has been burned, when the core is full of iron and there's nothing left to fuse, fusion stops. The outward pressure vanishes, and gravity takes over. The core collapses in less than a second. In that instant, the core's temperature spikes to billions of degrees, and the density becomes so extreme that protons and electrons are crushed together, forced to merge, forming neutrons. The core becomes a neutron star, a sphere of neutrons about 20 kilometers across, so dense that a teaspoon of its material would weigh 1 billion tons, more than all the cars on Earth combined. The collapse is so violent, so sudden, that it releases an enormous amount of energy, more energy than the sun will emit over its entire 10 billion year lifetime, released in a fraction of a second. That energy explodes outward, slamming into the star's outer layers like a shockwave from a bomb. The shockwave tears through the star at tens of thousands of kilometers per second, heating the gas to billions of degrees, blowing the outer layers into space. The explosion is so bright, that for a few weeks the supernova can outshine every other star in the galaxy combined. A single exploding star brighter than 100 billion stars, brighter than the entire Milky Way. When Betelgeuse goes supernova, it will be visible from Earth during the day. For a few weeks, maybe a month, you'll be able to walk outside in broad daylight and see a second bright point in the sky, not as bright as the sun, but roughly as bright as the moon at half phase, maybe brighter. At night, it will cast shadows, faint but visible. You'll be able to read by its light, hold up your hand, and see a shadow on the ground. It will be brighter than Venus, brighter than Jupiter, brighter than any star or planet you've ever seen. The supernova will remain visible to the naked eye for about a year, maybe longer. During that time, the expanding debris will glow, powered by the decay of radioactive isotopes produced in the explosion. Nickel 5-6 decays into cobalt, 5-6 which decays into iron, 5-6 releasing gamma rays that heat the gas and make it shine. Slowly, as the isotopes decay and the debris expands and cools, the light will fade. After a year, Betelgeuse will be invisible to the naked eye. After a few years, you'll need a telescope. After a decade, even the best telescopes will struggle to see it. The star will disappear from the night sky, leaving behind only a faint nebula, a glowing cloud of gas and dust spreading outward into space, expanding for thousands of years until it merges with the surrounding interstellar medium. At a distance of 650 light-years, Betelgeuse is far enough away that the supernova won't harm us. The dangerous radiation from the explosion gamma rays, X-rays, high-energy particles, will be diluted by the vastness of space. By the time it reaches Earth, it will be harmless, too weak to damage our atmosphere or affect life on the surface. There will be no mass extinction, no atmospheric damage, no ozone depletion, no threat to life. We'll simply have a front-row seat to one of the most spectacular events in the universe, a cosmic fireworks show that's completely safe to watch. But there's a catch, a wrinkle in time that makes everything strange. Because of the 650 light-year distance we're seeing Betelgeuse as it was in the year 1374, if the star exploded in the year 2000, we won't see it until the year 2656, 150 years after the actual event. If it exploded yesterday, we won't know for another 650 years. The light takes time to cross the void, and during that time the event is invisible to us, hidden by the speed of light. And that raises a tantalizing possibility, one that captures the imagination, one that makes you look at Betelgeuse differently. Betelgeuse might have already exploded. The light from the supernova could be racing toward us right now, crossing the emptiness of space at 300,000 kilometers per second, closing the distance. In 100 years, or 200, or 500, that light will finally reach Earth. And on that day, the night sky will change forever. Orion will lose its red shoulder. A new star will blaze in the darkness. And we'll know that Betelgeuse is gone, that the giant has fallen, that the star we've been watching for centuries finally ran out of time. Consider this: the star you see when you look at Betelgeuse is already gone, already dead, already history. You're looking at light that left the star in the Middle Ages, before the Renaissance, before the Age of Exploration, before the Industrial Revolution. The Betelgeuse of today, the Betelgeuse that exists right now in real time at this very moment, is invisible to you. It could be shining steadily. It could be dimming. It could be brightening. It could be on the verge of collapse. It could be exploding. You won't know until the light arrives, until the information finally reaches you, until the past catches up to the present. And when it does, when it does, it will be a reminder that the universe is vast, ancient, and full of events that play out on timescales we can barely comprehend. A star dies 650 years ago, and we learn about it 650 years later. By then, the explosion is history. The debris has already cooled. The neutron star at the center has already spun down, already faded. But for us, it will be new, immediate, a revelation happening in real time, even though it's centuries old, even though the star died before our grandparents were born. That's the strange beauty of astronomy. We study the past, but we experience it as the present. We look at the sky and see light from stars that may no longer exist, galaxies that have moved on, events that have already concluded. We're watching the universe's history unfold in real time, a cosmic movie that's always playing, always revealing, always surprising us with new scenes from the distant past. But beyond the spectacle, beyond the brightness and the drama, and the thrill of watching a star explode, Betelgeuse's eventual supernova will mean something deeper, something more profound. It will remind us where we came from and what we're made of. Every atom in your body came from a star, not metaphorically, not poetically, not as a spiritual concept or a comforting thought. Literally, every single atom, the hydrogen in your water, the calcium in your bones, the iron in your blood, the oxygen you breathe, the carbon in your DNA, all of it was forged in the core of a star, like Betelgeuse, then scattered into space when that star exploded. Billions of years later, those atoms drifted through the galaxy, clumped together under gravity to form the Sun and Earth, and eventually became part of you. You are made of stardust, not in a vague, metaphorical sense. In the most literal sense possible. The universe started simple. In the moments after the Big Bang, 13.8 billion years ago, only the lightest elements existed: hydrogen and helium with trace amounts of lithium. That was it. No carbon, no oxygen, no nitrogen, no iron. The periodic table had 3 entries. Everything else, every element heavier than helium, every atom that makes up rocks and water and air and life, had to be created. And the only place in the universe where that creation happens, the only forge hot enough and dense enough to build heavier elements, is inside stars. Stars are element factories, cosmic furnaces where hydrogen is transformed into everything else. In their cores, hydrogen fuses into helium, releasing energy, powering the star. Helium fuses into carbon and oxygen. Carbon and oxygen fuse into neon, magnesium, silicon. The process continues, building heavier and heavier elements, climbing the periodic table, step by step, until the core is full of iron. Iron is the end of the line. Fusing iron doesn't release energy, it consumes energy. Iron is the most stable nucleus, the element that sits at the bottom of the nuclear energy curve. You can't get energy by fusing iron into something heavier, and you can't get energy by splitting it into something lighter. It's a dead end, a wall that stars can't break through. So when a star's core fills with iron, fusion stops. The star dies. But in the final moments before death, in the last seconds of the star's life, something extraordinary happens. The collapsing core releases a flood of neutrons, subatomic particles, with no electric charge able to penetrate nuclei and stick to them. Those neutrons are captured by the surrounding atoms, adding to their mass-building elements even heavier than iron. Gold, silver, platinum, uranium, lead, all of them are created in the chaos of a supernova explosion, in the brief, violent moment when the core collapses and the shockwave tears through the star. For a few seconds, the core of the dying star becomes a cosmic forge, producing every element in the periodic table, from hydrogen to uranium, all the way up to the heaviest elements that can exist. Then the explosion flings all of that material into space. The atoms scatter, blown outward at thousands of kilometers per second, spreading through the galaxy. They drift through the interstellar medium, mixing with clouds of hydrogen and helium, cooling and clumping. Millions of years later, those clouds collapse under their own gravity, forming new stars and planets. And those planets inherit the elements created by the previous generation of stars, enriched by the deaths of giants like Betelgeuse. Earth is made of stardust. So is everything on it. The ground beneath your feet, the air you breathe, the water you drink, the trees, the mountains, the oceans, all of it is recycled star matter atoms forged in stellar cores billions of years ago. And so are you. The iron in your blood, the iron that binds to oxygen in your hemoglobin, carrying it from your lungs to your cells, keeping you alive every second of every day, was forged in the core of a red supergiant like Betelgeuse. It was created under temperatures of billions of degrees, under pressures so extreme that atoms were crushed together, fusing into heavier and heavier elements. And in the final seconds, before the star's core collapsed, that iron was blasted into space, thrown outward in a shockwave that reached speeds of 30,000 kilometers per second. That iron drifted through space for millions of years, maybe hundreds of millions. It mixed with hydrogen and helium in a molecular cloud, a vast region of gas and dust floating between the stars. About 4.6 billion years ago, that cloud collapsed, compressed by the shockwave from another supernova, and began to form a new star, our Sunday. The iron was caught up in the collapse, pulled inward by gravity, but not into the sun itself. Instead, it ended up in the disk of material orbiting the young star, the protoplanetary disk. Over millions of years, that disk clumped together, forming planets. Earth formed from that disk, and the iron ended up here, in the rocks, in the core, in the soil. And eventually, through billions of years of geology and chemistry and biology, some of that iron ended up in you. The calcium in your bones, the carbon in your DNA, the oxygen in your lungs, all of it came from stars. Different stars dying at different times, scattering their atoms across the galaxy. You're not just made of stardust. You're made of the remnants of dozens, maybe hundreds of dead stars, each one contributing atoms, each one adding to the mix. Carl Sagan said it best in a line that's been quoted a million times but never loses its power. We are made of star stuff. But it's more than that. We are the universe becoming aware of itself. The atoms in your brain, atoms that were forged in stellar cores billions of years ago, atoms that drifted through space for eons, atoms that have been recycled through countless generations of stars, are now conscious. They're thinking. They're asking questions. They're looking up at the night sky and wondering where they came from, wondering what they're made of, wondering if there's anyone else out there doing the same thing. And when you look at Betelgeuse, you're looking at a star that's doing right now what countless other stars did billions of years ago. It's fusing elements in its core. It's building carbon and oxygen and silicon, layer by layer, step by step. And when it finally explodes, it will scatter those elements into space, seeding the galaxy with the raw material for future stars, future planets, and maybe even future life. Somewhere billions of years from now, on a planet orbiting a star that hasn't been born yet, a creature might look up at the sky and wonder where it came from. And the answer, whether it knows it or not, will be from stars like Betelgeuse. Betelgeuse is a factory for the building blocks of existence. It's a furnace where the universe creates the elements necessary for chemistry, for planets, for biology, for life. Without stars like Betelgeuse, there would be no iron, no oxygen, no carbon. There would be no rocks, no water, no atmosphere. There would be no life, no consciousness, no one to ask the question, where did we come from? Every breath you take contains oxygen, atoms that were once inside a star fused from helium in a core hotter than the surface of the Sunday. Every time your heart beats, it's powered by iron that was forged in a supernova, created in the final seconds of a dying star. You are, in the most literal sense, the child of dead stars. You are their legacy, their gift to the universe, their way of continuing to exist after they're gone. And Betelgeuse will add to that legacy. When it explodes, when the core finally collapses and the shockwave tears the star apart, it will release iron, oxygen, carbon, silicon, magnesium, neon, and dozens of other elements into the Orion nebula, the vast cloud of gas and dust that surrounds the constellation. Those elements will mix with the existing gas, enriching it, adding to the chemical complexity. Millions of years from now, new stars will form from that enriched material, stars with higher metallicity, stars surrounded by protoplanetary disks full of carbon and oxygen and silicon. And those disks will form planets. Rocky planets with iron cores and silicate crusts. Planets with atmospheres of nitrogen and oxygen. Planets with oceans of water. And in those oceans, life might begin. Simple at first, single-celled organisms replicating molecules, the first stirrings of chemistry becoming biology. And over billions of years, that life might evolve, might grow more complex, might develop eyes and brains and hands. And one day, creatures might walk on the surface of that planet, breathing air, drinking water, looking up at the stars, wondering where they came from. And the answer, buried in every atom of their bodies, will be from Betelgeuse. Consider this: somewhere in the universe there's a planet orbiting a star that formed from the debris of a supernova that exploded 5 billion years ago. On that planet, there are oceans, continents, mountains, forests. There are creatures walking on its surface, breathing air, drinking water, living their lives. And none of them know that the atoms in their bodies came from a star that exploded billions of years ago. A star they'll never see in a part of the sky they can't reach in a time before their planet existed. In the same way, we are the descendants of stars we'll never know. Stars that lived and died long before the sun existed, long before the Milky Way looked the way it does now. Stars whose light has faded, whose names were never spoken, whose existence is known only through the atoms they left behind, scattered through the galaxy like seeds on the wind. Betelgeuse is one of those stars in the making. Right now, it's a red supergiant shedding mass pulsing, erratically nearing the end of its life. But when it dies, it won't disappear. It will transform. The iron in its core will collapse into a neutron star, a sphere 20 kilometers across, spinning hundreds of times per second, pulsing like a lighthouse. The outer layers will explode into space, expanding for thousands of years, creating a supernova remnant, a glowing shell of gas and dust visible for millennia. And those layers will carry carbon, oxygen, silicon, iron, all the elements needed to build new worlds. The atoms that make up Betelgeuse will drift through the galaxy for millions of years. They'll mix with gas clouds, they'll collapse into new stars, and someday, billions of years from now, those atoms might become part of a planet. They might become part of an ocean. They might become part of a living thing. A tree, a fish, a bird, a creature with eyes and a brain capable of thought, capable of wonder. And that living thing, if it has eyes, if it can see, might look up at the night sky and wonder where it came from. It might see a galaxy full of stars, some bright, some dim, some red, some blue. It might see constellations, patterns in the darkness, shapes imposed by biology and culture and imagination. And it might ask the question that every conscious being asks, the question that defines what it means to be aware: where did I come from? And the answer, written in every atom of its body, will be from stars like Betelgeuse, from giants that lived and died billions of years ago, from furnaces that burned for millions of years, fusing hydrogen into everything else, building the periodic table, one nucleus at a time, from explosions that scattered those atoms across the galaxy, seeding space with the raw materials for planets and life. That's the legacy of Betelgeuse. Not just a dying star, not just a supernova waiting to happen, but a link in the chain of cosmic creation, a furnace that transforms hydrogen, for the simplest element, the element the universe started with, into the complex elements necessary for existence. When Betelgeuse dies, when it finally runs out of fuel, and the core collapses, it will give birth to a new generation of stars. And in doing so, it will continue the process that created us, the process that turned a universe of hydrogen and helium into a universe of planets and oceans and life. We look at Betelgeuse and see a red giant in Orion, a star marking the hunter's shoulder, a point of light 650 light-years away. But Betelgeuse sees us too, not as individuals, not as people, but as the distant future. The atoms it's creating right now in the furnace of its core will outlive the star by billions of years. They'll drift, clump, fuse, and eventually become part of something new. Something that doesn't exist yet. Something that can't be predicted. A star, a planet, a moon, a comet. A rock, a drop of water, a blade of grass. A cell, a creature, a thought. And when that something looks up at the stars, it will see a universe full of light. Light from stars that are dying, stars that are being born, stars that are forging elements in their cores. And it will know, consciously or not, intuitively or through science, that it came from those stars, that it is made of their atoms, that it is their legacy. We are stardust looking back at the stars that made us. And Betelgeuse, strange, dying, unpredictable Betelgeuse, is one of the stars that will make the future. When it explodes, it will scatter the building blocks of existence across the galaxy. And somewhere, someday, those building blocks will become part of something alive, something conscious. Something that looks up at the sky and asks, where did I come from? And the answer will be from Betelgeuse.